Okay guys, let's try a curve sketching problem. This was number 6 off of the worksheet, and I'm just going to remind you that right now I'm going to use the quotient rule, derivative of the first times the second minus derivative of the second times the first all over the second squared. And after I simplify this, I'm going to find the second derivative, most likely also with the quotient rule. So I'm going to pause my recording and then pick it right back up once the derivatives are done. Okay, so here are your two derivatives. Check and see if you got the right things, and if you need to pause this to help you fix your work, then go ahead and pause it. Once I simplified the first derivative, I then used the quotient rule, derivative of the first times the second minus derivative of the second goes all the way up to here because of the chain rule, times the first all over the second squared. And then you can see that it's really sort of a must at this point to find the fact that this quantity is repeated throughout the terms. So you can cancel one of these from every single term, or basically factor one out of the top and cancel it with one of them on the bottom. And then finally you can get to this step. All right, so once we have our two derivatives, we want to use them to get your extrema and your concavity. There is something we're going to have to go back and talk about, but let's start. So we'll take the first derivative and set it equal to 0, which you can hopefully see is going to give you a non-real number. But we had to at least consider it. So now we're going to take the denominator of the first derivative, and we're going to set that equal to 0 because that is what makes the first derivative undefined, and those are also our critical numbers. So you can square root both sides, then moves the 16 over, and we see that we get plus or minus 4. So why do we want those numbers? Because we want to figure out that on those are our critical numbers. So on either side of our critical numbers, what happens to the function? So we're going to take something back here and plug it in. So I'm going to try maybe -5, and then I'm going to try a 0, and then I'm going to try a 5, and I'm going to plug that into my first derivative. If I notice that the top is always, the numerator is always positive. You're squaring something, multiplying it by 3, and adding 48. So the numerator is always positive, so all I have to worry about is the denominator. Well, look, the denominator is always positive. Whether x squared minus 16 is positive or negative, once you square it, it's always positive. So all three of these evaluate to fractions where you have a positive over a positive. So that means that our function is always increasing. So we have no relative extrema. Okay, the next thing we're going to look at is concavity. So remember, for that we're going to use the second derivative. We need to set the numerator and the denominator both equal to 0. I've done that here already. And then from there it's simply algebra. So I noticed that I could factor a 6 out of 288, or 6x actually. So I'm factoring out a -6x. This is what I'm left with. And then similarly to when we were finding extrema, we can cube root both sides here instead of square root, and then move the 16 over, and we get x equals plus or minus 4. Notice that from this part, I'll get x equals 0 or x squared equals -48. And x squared equals -48, again, will not give you a real solution. All right, now I've already made my number line and put my numbers where the second derivative is 0 or is undefined on the number line. Maybe let's remind ourselves that we're plugging values that are in between these numbers into the second derivative. So I've drawn little fraction bars, again, to remind us that we just need the signs. We don't need actual values. And I'm going to use this fraction. So the numerator comes from right here. Now, since this part will always be positive because you are squaring a number and then you're adding 48, all I have to realize for the numerator is what's going to happen when I plug one of these numbers into -6 times that number. So a -6 times a -5 will be positive, and -6 times a -3 or a -1 will be positive. So both of these numerators will be positive. Over here, I'm going to plug in positive numbers like +1 or +5. When I take negative 6 times 1, I get a negative. When I take negative 6 times 5, I get a negative. So those are my numerators. Now let's look at the denominators. Well, the denominators, now I have x squared minus 16 cubed. When you're cubing something, you can go negative. So let's take a negative 5. Negative 5 squared is 25. 25 minus 16 is positive. A positive cubed is a positive. If you will, follow me over here. Same thing happens when you plug in a positive 5, right? You get 25 minus 16, which is positive. Cubed is positive. Now, it's these values in here that are going to maybe be different. So if I take a negative 1 squared is positive 1. 1 minus 16 is negative, and a negative cubed is a negative. And that happens whether you plug in a negative 1 or a positive 1. So now I have these fractions, right? This is where I'm going to get the sign of the second derivative. A positive over a positive over a negative. Negative over a negative, negative over a positive. Because again, this was a second derivative that I was looking at, that means I'm going to be concave up, down, up, down. Now finally, we might get to what did we not do here yet. So we could tell that concavity switches here, here, and here. And so that means at this point we want to look at points of inflection, right? Now if we look at negative 4 something as being a point of inflection, we have to plug in the negative 4 to the original function. Well, if we do that, we get a positive 12 over 0. So what we never did was we never talked about our vertical asymptotes and our horizontal asymptotes. But because when I plugged in a negative 4, I'm actually getting a non-zero number over 0. 4 was actually a vertical asymptote. So was x equals positive 4 and negative 4. Those are both vertical asymptotes. So those aren't going to be points of inflection. But let's try putting in 0. I mean, it is a concavity switch. It's just not a concavity switch at a point. So what happens when we plug in 0, again, to get the y value? We get 0 over 0 minus 16. Well, that's 0 over negative 16, which is 0. So 0 over 0 is a point of inflection. Now again, plus or minus 4 actually were asymptotes. So they're places where the concavity switches, but they are not points. So finally, let's go back up here and see. So we found vertical asymptotes. Where are our horizontal asymptotes? Remember that in Blackboard in your resources folder, there is the chart that reminds you the shortcuts for finding horizontal asymptotes. The shortcuts come from actually finding the limit of this function as x approaches infinity. So because the numerator has a smaller degree than the denominator, this has degree 1, this has degree 2, our horizontal asymptote is at y equals 0. Putting all of this together, that's the end goal, we have two vertical asymptotes at negative 4 and positive 4. We have a horizontal asymptote at y equals 0. We have a point of inflection at 0, 0. And that's about all we can label. So now what do we do? Well, I like to let concavity be my guide, but also here, if you look at the fact that the function is always increasing, that also helps. You're going to be following asymptotes. If the function back here before negative 4 has to increase, would this increase or would this increase from left to right? Hopefully you would agree that this is the one that increases. Does that match what happens here? It sure does. It's concave up. So there's the part of the graph back here. I wanted to make sure I didn't make that swing back up to make it look like I had an extreme value. Okay, between negative 4 and 4, I have a point of inflection. Before or to the left of that point of inflection, I want the graph to be concave down, and to the right of that, I want it to be concave up. I also want to follow my vertical asymptotes, and I would like my function to always be increasing. Well, lo and behold, if you try to make all of these be true, look, we have an increasing function that's concave down, and then we have an increasing function that's concave up, and we do follow our asymptotes. The last part, we want our piece of the graph to be concave down, so that should be making you think, okay, it's down here. Let's check and make sure this is also true. Would the function be increasing here from left to right? And yes, it would. From left to right, we're increasing. So that is a curve sketching problem where we have both vertical and horizontal asymptotes, and if you did not find these, probably it would have been quite the challenge, to correctly sketch this curve. All right, so hopefully this example helped.